now let's expand beyond the notion of just the basic hydrogen atom into atoms that we don't know how to solve exactly, but we usually have a general idea for writing those down, right? So the idea being that, going back to that classical picture, you have like a bunch of different electrons in different electron clouds orbiting the nucleus in a bunch of different ways. You probably learned in high school chemistry that the reason that you have the periodic table is the Pauli exclusion principle, basically saying that no two electrons can occupy the same state. So why is it that no two electrons can occupy the same state? Why isn't it the case that every electron can occupy the lowest energy state in an atom? And the reason is that electrons are fermions. What is a fermion? A fermion is a spin 1/2 particle. What is a spin 1/2 particle? It's a fermion. It's a little bit of recursive logic. What is this notion of spin, I think, is the more important thing. And spin is this, it's not an actual thing. It's not like the electron is like spinning as it's going around an atom. It's really a quantum mechanical construct that we use to describe a certain property that the electron has. The main difference being that, again, electrons are fermions, which means they have half integer spin, whereas there are these things called bosons that have full integer spin. And it all has to do with it's an eigenvalue problem. Going back to Math 51, it has to do with the solutions that you get when you apply an operator and diagonalize the Hamiltonian and get a solution, right? The main difference between the two particles, for those of you who don't care about matrices, being that fermions cannot occupy the same state, whereas bosons can. Given the opportunity, two fermions cannot occupy the same state. State in this case meaning atomic energy level, whereas two bosons can. The reason for that is that fermions must have an anti-symmetric wave function. Yeah?
So why are electrons fermions instead of bosons? Okay.
Cool. I knew someone was going to ask me that question, and I wanted to have like a really good answer to it. The only response that I have is that you should go watch the Richard Feynman video where he talks about like why are magnets magnetic, right? Or like why are there magnetic fields? Like asking why an electron is a fermion is like asking why the color blue is like a certain nanometer thing. Like it just is. There's no necessarily like reason for it being one way.
What's a boson? What's an example of a boson?
So bosons are things like photons. They're in particular, like in the standard theory of particle physics, they're called gauge bosons, which are force-mediating bosons. So it's things like photons, phonons, any sort of force-carrying particle. Yeah, graviton. So the interesting thing is those are spin 1 particles. The graviton is actually theorized to be a spin 2 particle, which is why things like electromagnetism, which are mediated by photons, are attractive and repulsive. Whereas spin 2 theory leads to gravity only being an attractive force and never a repulsive force. But that's currently a theory. They have absolutely no way of proving that. So the key thing is that because electrons are fermions, because if you were to take 2 electrons and exchange them, their wave function would disappear. That doesn't necessarily make sense, but know that electrons are identical particles in the sense that you can't like paint one red and paint one blue and then like follow them as they go along. They're absolutely identical. But the problem with electrons is that if you try to switch them, really, really bad stuff happens. They don't like occupying the same state. Whereas with bosons, they're perfectly comfortable being switched around and all occupying the same state. So if electrons were bosons, we would have a really boring periodic table because it would only have one element, and that would be one electron or however many protons in the middle with however many electrons orbiting those protons in the exact same energy. The only reason you get so many different elements is because of the Pauli exclusion principle that prevents 2 electrons from occupying the same state. For those of you who also remember basic chemistry, the reason you can have 2 electrons in the lowest energy level is that we have this notion of spin up and spin down. And the fact that one electron can be spin up and another can be spin down allows 2 electrons to occupy the same energy state but no more, which is why the periodic table builds up roughly like, that looks like a penis, like that, where you can fill up each box with spin up or spin down, SPF and all those different orbitals and stuff. And going back to part 2, which I'm going to make vague sweeping generalizations and not really talk that much about it, is one of the reasons why materials don't necessarily pass through one another A has to do with the Coulomb interaction. Obviously, you've got electron-electron repulsion between the electron shells of different materials as you try to like push things through together. But the reason that materials aren't as denser than we find them to be in the real world has to do with this notion of exclusion, the fact that electrons don't like to occupy the same state. And they've actually done this. There's a nice picture in this book, which is Cattell, and I'll show it because my drawing ability is just phenomenal. Where if you try to have two electron wave functions overlap, so you can sort of see over here, you've got this like probability distribution basically for what electrons look like. If you try to make them overlap, they don't like it. They go into a higher energy state because they can't occupy the same energy state. And it's actually measurable. It's on the order of something like 20 eV. Like it's a large amount of energy that you find if you take something like two hydrogen atoms and try to make a helium atom. They really, really don't think it. Yeah.
So this seems weird. It's like an electron inside a certain atom cares about the electrons around it. Like changing the electrons around will actually change the properties of that electron.
Yeah, for sure. Well, not the properties of the electron itself, but like this shouldn't be that weird because you have this idea of like a metal where they just share a bunch of electrons between them, right? The like valence electrons that can go throughout stuff. So the electrons in one atom can definitely affect electrons in the material around it. The main thing is that if you try to bring two of them closer together, you actually find, and the reason that I'm not showing to you is because it's really difficult to calculate this. It wasn't done until the last like 30 years by a guy named Ed Lieb in Princeton, who's a mathematical physicist. But you get this thing called the exchange interaction or the exchange force, which actually leads to like a repulsion between the two things. So again, if electrons were bosons and everything were boring because everything was just one element, you wouldn't get that repulsion and everything would be a lot more dense. The other thing would be that you could theoretically have things occupying the same state, which means you could walk through a wall like a ghost and theoretically emerge on the other side because your particles would be occupying the same state in the same space as all of those other particles, and you could just sort of like walk through and hang out with them.
Wait, so you said like physical matter is made up of bosons, or
fermions? Yeah,
fermions.
Both protons and electrons are fermions.
Okay, and they can't be in the same space.
They cannot be in the same state.
Okay, what are example of bosons? So like photons and stuff like
Yeah,
that?
photons.
So can a photon and a boson occupy the same space?
It's only with identical particles that you actually care about it, because an electron is fundamentally different from a different spin 1/2 particle like a proton.
Okay.
So it doesn't really care as much because those are theoretically distinguishable, right? A lot of this has to do with the concept of distinguishability, right? Like the reason that two identical electrons can't occupy the same state is because this idea of anti-symmetrization, right? When you swap them, bad things happen, right? Like it doesn't allow you to swap them without sort of any energy.
Yeah.
It's difficult for me to explain because I don't fully understand it. But it's not the same for an electron and a proton because they're not identical particles. You can keep track of where it's going. If you guys take like thermodynamics or statistical mechanics, you'll deal with this idea of distinguishability, and you'll actually see that there's a very profound effect on the energy of the system. Did you have a question?
So this is why you can make a laser out of electrons.
Yeah, this is why you can't make an electron laser, because the whole principle of a laser is that you're using the fact that photons are bosons, and you're putting them all in the same coherent state. And they propagate as one giant wavefront, basically, all, having a good time.
And so, can bosons then pass through fermions? Because how does light come through a window?
So, well, that's that's a totally different thing. That has to do with actually like light is not just coming through a window. Like it is it is passing through a lot of stuff.
But light passes through light without interacting with it.
Yes.
Which is so like the reason you can't walk through a wall is because you're made of fermions and the wall is made of fermions. But if you had a sheet of light and you shine light through that, it can go right through it.
Right, but
Because the bosons can occupy the same energy.
That has to. So your question has to do with like materials and crystallography, right? And the reason for that, I'm not as intimately familiar with, but there are good reasons for it. It's not actually just like passing through, though. Things like neutrinos, for example, right? Like there are millions and millions of neutrinos passing through our bodies every second. Those, I believe, are actually spin 1/2 particles, or fermions, not bosons, but they're just very, very weakly interacting. They have a very, 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 very small mass.
Yeah, that's what I was kind of asking when I was asking if bosons and fermions can like pass through each other or not. Because so is it just that like when light passes through a window but not through a wall? Is it that like there's something about the arrangement of the atoms there that like
yes,
that,
but
the light is passing around it? Or
that has less to do, I think, with the arrangement of. That has less to do with bosons and fermions
so
than
it's
it
not
does
about-
to do with the actual arrangement of atoms
that's
and
what
the
I was
properties of that particular material. I'm talking more about broad sweeping generalizations about materials in general. Why they're not super dense. Anything else? I went way over time, and I apologize for that.
Are we
You done?
Yeah, we're done. Yeah.
No, it's alright. It was good.
Okay.
It was really interesting.
We could have just done the Heisenberg certainty principle for like 2 hours.
Yeah.
Sorry.